Hello, this is Professor Kuehn. Let's do one more problem on projectile motion. You might remember that in our last couple of problems we worked out, we were dealing with a situation where a projectile is launched horizontally from atop a cliff, and we're determining the range. I think, in fact, we were trying to determine the muzzle velocity of the cannon given the range and the height of the cliff. This will be a little bit of a variation. What's different about this problem is that we're going to be imagining a cannon or a gun that is fired from a horizontal surface, landing on the same horizontal surface like a big field, but it's going to be fired at a diagonal, that is at some elevated angle above the horizon. So imagine a situation like this. We have the ground here, a flat surface, and we were to fire a projectile from ground level. This will represent the projectile, and it's going to be fired with an initial velocity at an angle like this. And let's suppose we're given that the muzzle velocity, V0, is 600 meters per second. And furthermore, let's suppose that the angle that it's being fired at is 30 degrees above the horizontal. Okay, so you might imagine a gun that's very low placed to the ground and firing at a diagonal like this. And what I want to do is ask two questions. And you might start trying to think about how you might answer these as I'm writing out these questions. So the first question is, what is the maximum altitude that this bullet achieves? So what is the maximum height that it gets to before it turns around and comes back down? And the second question is, what is the range? What is the range of this projectile? How far horizontally does it get before it strikes the ground? As with Galileo, we are going to make the simple assumption that drag plays no role here. Again, this is a simplification, in fact, an oversimplification. When you're firing a projectile, in fact, drag does play an effect. But we can always add that complication back in later if we'd like to. We're trying to get to the essence of this problem by ignoring drag for the time being. Okay? The other assumption we're going to make is that the horizontal and the vertical components of the motion are, in a sense, independent of one another. That is, we can treat the vertical motion separately from the horizontal motion. So we're going to break this problem into a vertical problem, you'll see what I mean by that in a moment, and a horizontal problem. And then at the end, we'll put things back together. Okay? So here we go. What is the maximum altitude achieved by the projectile? Well, the altitude is determined by the vertical velocity, that is how fast you're throwing it upward. So in order to address that problem, we need to consider, so here's the answer to question 1, we need to imagine the velocity as being decomposed into a vertical part and a horizontal part. So this is the muzzle velocity, this is the vertical part of the velocity, and this is the horizontal part of the velocity. And we, again, know this angle in here to be 30 degrees. So how do we figure out the vertical component of the velocity given this 30, 60, 90 triangle and the hypotenuse? Well, you might imagine we can use trigonometry. So remember that sine of theta is going to be opposite over hypotenuse. So that sine of theta would be the opposite, would be the vertical velocity, and the hypotenuse would be the muzzle velocity. And that implies that if you want to solve for the vertical velocity, you take sine of theta times the muzzle velocity. That would give us its vertical speed, okay? And now keep in mind, if this is a 30, 60, 90 triangle, let me remind you of the properties of a 30, 60, 90 triangle. The length of the sides is 1 to 2 to root 3. That's the ratio of the sides. So if you have sine of 30 degrees, that's 1 over 2, opposite over hypotenuse is 1/2. In other words, the vertical velocity is going to be 1/2 of the hypotenuse length, or since the hypotenuse is 600 meters per second, the vertical component of the velocity is 300 meters per second. Okay, so that's going to be an important piece of information. Now we know how fast it's being thrown upward. Now the trick here is to consider, to get the height of this, all we need to do is figure out the moment that it has lost all of its vertical velocity. How do we do that? Well, I'll make a sketch here just to remind you of how this works. The vertical velocity as a function of time, since it's undergoing uniform acceleration, it's losing speed at a constant rate. And if its initial vertical velocity is 300 meters per second, and the slope of this, which is the acceleration, is -10 meters per second squared, that it's losing 10 meters per second of speed every second. I know I'm rounding off to 10, but we typically do that in this class. And from that, we can figure out the time it takes to get to its peak. That is the time in which it will lose all of its speed. So another way to think about this is you can solve for this time, t1, the time it gets to its peak, by taking its vertical velocity, which is 300, and dividing by the slope of this, which is 10. Okay, 300 meters per second divided by 10 meters per second squared, and that would give us a time of 30 seconds. So this is a bit maybe unrealistic. It takes 30 seconds for it to come to its peak, but there we have it. It's 30 seconds to its peak. Okay. Now, how do we figure out the height that it gets to? Well, the maximum height that it reaches is just going to be the area under this right here. Okay, and there's a few ways to do this. Let me do it using the mean speed theorem. What we could do is we could say this moves the exact same distance as another object would have moved if it's going for the same time at the mean speed. Okay, so we find the area of that rectangle. Well, that's pretty easy because the mean speed would be 150 meters per second, and the time we just saw was 30 seconds. And so the distance, or the height that it gets to, would be 150 meters per second times 30 seconds. Well, that gives us 4,500 meters, or 4.5 kilometers. So that's pretty high. Okay, so in the absence of any air resistance, this thing would get to a height of 4.5 kilometers. Okay, now what about answering the second question? Answer 2, what is the range of the projectile? Here we have to use once again the fact that the vertical motion in no way affects the horizontal motion. The horizontal motion is just a uniform motion. It's not accelerating in the horizontal direction. So whatever speed it had originally in the horizontal direction, it maintains the same speed. Well, how do we figure out the horizontal speed? Well, the horizontal speed is gotten once again from this triangle. And this time we're going to use cosine of theta. Remember that cosine of theta is adjacent over hypotenuse, and the adjacent angle is the horizontal speed, the hypotenuse is v0, and so using algebra, we find that the horizontal velocity is going to be cosine of theta times v0. Well, what's cosine of theta? Cosine of theta is adjacent over hypotenuse. That's √3/2 times 600 meters per second. And so we get that the horizontal velocity is going to be equal to, well, √3 times 300 meters per second. And I don't have a calculator handy, so I'll just leave it in that form. Okay? And now what we can do is if we want to find the range, all we need to do is multiply that horizontal speed by the time that it's in the air, the time of flight. So what is the time of flight? The total time of flight is going to be, well, we know it took 30 seconds to get to its peak, so it's going to take 30 more seconds to get back down to the ground, so it's going to take 60 seconds. It's going to be in the air for 60 seconds, and so the range of this projectile is just going to be the horizontal velocity, which is √3 times 300 meters per second times 60 seconds, and that will be the distance in meters. Oh, and so you get √3 times 1,800 meters. Okay, and so that would be the range of this projectile. There you go. We have just solved for the range of the projectile and the maximum height of the projectile. I hope these problems help you in solving the kind of problems you'll be doing in lab this week. Have a nice afternoon.